Hi, my name is Dr. Martin Bell and I'm an astrophysicist here at UTS. I wanted to spend a bit of time today exploring what a normal distribution or a Gaussian distribution was and how it relates to the number of hotter days we may receive in Sydney in Australia with a warming climate. Now, my motivation for doing this was that I've become quite concerned in the last couple of months about the situation unfolding in Sydney and in Australia with the bushfires, and I've been asking myself how this is related to climate change and what may happen in the future. So for me it was just trying to explore some of the basic physics and trying to understand that, and trying to sift through some of the posts that have been put on social media to understand what's true and what's false. So before we get into everything, let's have a basic look at what an actual physicist does and why we use graphs and equations to explain the outcomes of situations. And one of the most simple cases that we can have is a one-to-one relationship, which is, if we plotted a graph of it, we could plot some variable on this axis here and some variable on this axis, and a relationship which relates how one varies with the other. This one-to-one relationship is the sort of thing that you would study in HSC or A-level type physics if you were in the UK. And a common equation we might write for this is if we wrote x on this axis, actually, sorry, I've got that wrong. Let's write t on this axis and let's write x on this axis. And if I wrote the equation x equals vt, we would find that for a certain amount of time, so if this was the axis for time, and this was a car traveling and moving forwards, as a larger amount of time elapsed, the distance x that the car travelled just moves linearly up. And the relationship between the gradient, which would be this curve here, would tell us how fast this car would increase. So this would be proportional to the velocity, what we could call this here. That's one of our most basic linear relationships that we deal a lot with in physics. The second one that's important, and there's many of them that are very important, is what we call a 1 over r squared relationship. Okay, so if I wrote intensity on this axis and I wrote radius or some distance on this axis, the way a 1 over r squared relationship works is that the intensity I might receive from something drops off as 1 over r squared. Okay, so let's just write that equation down. It says 1 over r squared. And let's just put some numbers into that, okay? And the best example of this in physics would be either gravity or radiation. So I'm sure you've all sat by a fire, sort of relevant to the bushfires, is if you put your hand closer and closer to that fire, the amount of heat that you receive on your hand doesn't just linearly increase, it gets very intense as you get your hand closer to the fire, and that's represented by this curve here. This would be very close to the fire and this would be very distant away from the fire. And if you put some numbers in here, if this was 1 unit away, the intensity would be proportional to 1 over r squared, so that'd be 1 over 1 squared, which equals 1. But as we move to a distance, say 2, these just units I'm making up, we would get 1 over 2 squared, which is equal to 1 over 4. So you'd get a quarter of the intensity that you'd once initially received. So those are two of the most basic equations and physics relationships we use to explain simple systems. Why do we like equations at all? They're really convenient for me to say to another physicist, instead of me saying something's going up, something's going up, something's going up in lots of words, I can say x equals vt and tell him everything he needs to know about, or he or she needs to know about that system. Now, let's move on to the bell curve, or the Gaussian distribution. And this is a more complex relationship, but it's very important that we understand it. It's very important we understand it in the context of temperature, but I'm going to give you a few other examples in physics of how this bell curve works. So if I draw this bell curve, it looks something like this, and it's called a bell curve because it looks like a bell curve. And this, I'm going to write on this axis here, t and n. So this is going to be the n number of something, and I'm going to put temperature on this axis. Now if you think about this in relation to my example here, let's just think about this. If this axis represented how hard I push my foot on the accelerator of a car, okay? If you had a real car, you would expect the harder you pushed it, the faster you would go. But what this distribution tells us, or what this line tells us, imagine this, I push my foot harder and harder on the foot pedal, I go faster, 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 and then at a certain point, I stop going any faster, and then actually I slow down. And that's what a Gaussian distribution does, or sometimes called a normal distribution, or a bell curve Gaussian distribution. It contains the things that I'm trying to measure within some certain range. And it's really, really useful for physicists to use this equation. And if you come to a physics department, one of the first questions we'll ask when we meet a piece of data is it Gaussian? It's like our triaging in an A&E department. We're trying to say, what does this data look like? Is it linear? Is it 1 over r squared? Is it Gaussian? And that tells us straight away what we're dealing with and how to deal with it. Now this thing has got a much more complicated equation. If I write down here, we don't need to know what this is, but we can write down this equation here, which looks something like this. T to the minus mu over sigma squared. Okay, so this is horrendous, and it's why we don't really meet the Gaussian distribution till sort of university level physics. But contained within this equation, it tells me how to predict the behavior of this line. And it tells me how to predict it based on a few things. One, which is sigma, the sort of distance between these side peaks, and the mean, which is mu here. Okay, that's a bit heavy on the maths, but let's have a look at some real distributions and how they work in real life. So the first one I've got here is the birth weight of children, okay? So birth weight of babies. And if we look at this distribution, what we'll find is this is actual real data that we've plotted here, and we've got my theoretical distribution predicted by that equation. You can see that the data fits really, really well. In the center here, I've got some mean birth weight of 3.39 kilograms, and at either end of the distribution, I have babies that are born at 1 kilo and up to 5 kilos, okay? Now, it's not something like a linear relationship where this just keeps going, like the size of babies being born has to be contained within some region, and the Gaussian allows us to do that. Here's another weird example I found on the internet. The heights of 3,000 adult English male criminals measured around 1900, okay? It's, again, follows a distribution. I'm not gonna find one of these people that is 9, 10, 20 foot tall, or under 3 foot. They're going to have a standard sort of size and range, and a width of that range. And that's what the Gaussian distribution gives us and allows us to do. Now, here's the worrying thing for temperatures. If we take the basic Gaussian distribution, I'm going to jump off this page here, and I'm going to draw it a bit bigger, okay? So let's draw our Gaussian distribution, and this is how temperature works, okay? So if I draw temperature on here, and the number of days I might receive at a certain temperature. In the centre for Sydney here, you might say that our average temperature is, say, 28 degrees. This is averaged over a whole year within a certain region, something like that. Now, imagine that this bit here was, imagine that this section here represented 40 degrees, and this tail distribution here represented something like 16 degrees, okay? So that's the number of really cold days I receive, are not very many, and the number of very hot days are not very many either. So let's just shade in that region here, okay? So we could say the area, the number of days that we receive over a certain thing, we could say that this maybe is 5 days, okay? Within 1 year we might receive 5 days that are over 40 degrees. Now this is the tricky bit with the Gaussian distribution. What happens if I shift that? Simply in the mean, if its mean shifts by a degree. So let's just replot this thing. I'm going to exaggerate it, but let me just replot this, okay? And I've probably shifted that a bit too much, but let's just exaggerate that. Let's just say that that's a 1 degree shift. It's not, it's about 4 or 5 degree shift. And then let's reshade in the number of hot days that I would receive. Would look something like this, okay? So based on a very small shift in that distribution, what I get is, I worked this out earlier, you might get another 3 times or 4 times. So you might then suddenly get 20 days above 40 degrees. And that's what's worrying about this distribution. You do not want to move it around, even by small amounts, because this shaded area here, the number of days I get over 40 degrees, increases non-linearly, okay? So that's how the Gaussian distribution works and how it changes if we shift it. One of the positive messages I wanted to sort of put out with is, how do you stop getting these really, really hot days? Is where you don't let this distribution shift. Now that's a much more complicated situation to solve, and related to climate change and the such like. But at the same time, the way the physics works is, don't let this Gaussian distribution shift in that direction. So what I had here as well was a number of other plots. Let's just have a look at. Okay, so this plot here shows us how our temperatures have looked over the last 100 years in Australia. So this is the mean temperature in January. and whether it's moved above where we expect it to be or below. And you can see we have a lot more days below in the last couple of hundred years, and more recently we have a lot of days that are a couple of degrees above where we want them to be. And this is the worry here. Without knowing anything about climate change, I know that simply if I get days that are a couple of degrees shifted in one direction, I'm going to get a larger number of hotter days within my summer. Now, I'm not an expert on how fires start, but I do know as a physicist that I would rather have less number of hot days to perpetuate the fires that we've seen in Australia. Looking at some actual data, this is some data taken from NASA, which I looked up, and these are just simple bell curve distributions for decades since the 1950s, and you can absolutely see this distribution shifting. So this is 1951 here in red, and again, if I do the trick with shading in the number of days, hot days if you like, under this distribution, and then link it with how these have shifted in the last sort of couple of decades, this is really worrying. What's interesting about the distribution as well is that it's flattened and spread out, so you actually get some cooler number of days, which is predicted by the physics underneath this distribution. So that's all I really wanted to say. I think it's important to understand that in everyday life, this Gaussian, this bell curve distribution is playing out, and as you shift it around, you can very simply understand how we might expect slightly different changes sort of underneath this distribution. And really what I wanted to talk about next time is that this Gaussian distribution pops up so many times for physicists. When we talk about how confident we are in measurements, you can again bring this Gaussian distribution in to tell us how significant a certain event is, and that's really important with reading the IPCC report when they say that they're highly confident in a measurement. And I'd really like to explore how we use the bell curve to detect very significant events.